Let's solve this question. This is gate 2000 question. Let PS denote the power set of set S. Which of the following is always true? Okay, so some statements are given to you and let's see which of them is always true. Let's see the option D. Option D is saying that S does not belong to power set of S. So first of all, let's look at option D. And this is the option D, that S does not belong to power set of S. This is definitely false. This statement is definitely false, because remember, it will always happen that S will always belong to power set of S. This statement is always true. This statement is always true. Why? Because S is subset of itself. We know that every set S is a subset of S. So what you can say that S will definitely, in the power set you will definitely have S. So this S will definitely belong to power set of S. So I can say this option D, this is actually never true. I can say this option B, option D, this is never true. Never it is true. Okay, so this is the idea, because S will always belong to power set of S, because S is subset of S. For any set S, I can say S is subset of S. You notice that phi is a subset of every set. Also, every set is subset of itself. So these two things we know. Now from this I can say that phi will definitely belong to every power set. Okay, so these two statements will always be true. These two statements. Okay, so as every set will belong to its power set, and also phi will also always belong to power set of every set. Okay, so phi and these two, so these two statements are always true. So I can say this option D is never true. Okay, let's see the remaining statements. The option C is saying that power set of S intersection S, that is equal to power set of S. That is also wrong, because you can clearly, okay, just take one example, and with this example you can eliminate many options. For example, let's assume you have a set S, and in the set S, let's assume this is the set S. Then what will be the power set of S? Okay, for this set, the power set of S will be, okay, there are two subset of S. This is the subset of S, and S itself is the subset of S. So this is your power set of S. In you can notice in the power set of S, one element is empty set, another element is S itself. Okay. Now what is S intersection power set of S? Is there any element that is common? There is no element common. You can notice in this S, this is the element. Okay. And in this power set of S, this is the element, this is the element. You can notice there is no element common. Remember, this A belongs to S, but remember this element does not belong to S. This does not belong to S. Okay, I can say that this element actually belongs to power set of S. But remember, you can see that this does not belong to power set of S. So these are the things that you can very easily see. Okay, so you can notice the set S and power set of S, they do not have anything in common. So their intersection will be phi. Okay, so their intersection is clearly not equal to power set of S. So I can say that this option C, this is wrong. Okay, but is it possible that option C can be true? See, option C is wrong, but can I say this will always be wrong? This is the question. Can I say this will always be wrong? Okay, so this is option C. We have already seen that option C is wrong, because you can notice for this example, for this set, you can clearly see that S intersection power set of S, that is not equal to power set of S. So this statement is wrong, we have seen. But my question, this is my question, that is it possible that this can be true for some S? Like, okay, is it possible? Can I say that this is always false for all the set S? Basically, the question is this: is there any set? Is there any set S? Is there any set S for which this becomes true? For which option C becomes true? Think about it. Think about it. Is there any set S? Do we have any set S? Is there any set S for which option C will become true? The answer is very simple. Answer is actually no. Why answer is no? See, okay, you have this power set of S. If set S has cardinality n, then what will be the cardinality of power set? That will be 2 power n. Okay, so if set S has cardinality n, okay, and you can notice that for any set, this n is basically greater than equal to 0. So this is the idea. You have a set S, okay, and let's assume the set S has cardinality n. Clearly this n is greater than or equal to 0. Okay, because this set should have, this set can be empty. In that case n will be 0, or this set is non-empty, then in that case n will be greater than 0. So this n is definitely greater than or equal to 0. Then what can you say about the cardinality of power set? The cardinality of power set, that is 2 power n. So if n is greater than or equal to 0, then basically 2 power n is greater than or equal to 1. You can clearly see that 2 power n is always greater than n. This 2 power n, this is always greater than n for all n greater than 0. For all n greater than equal to 0, you can notice that. So what I can say, basically this is what I'm saying. I'm saying that the cardinality of the power set will definitely be greater than the cardinality of set. It will always happen. For every set this will happen. If your set S has n elements, then power set will have 2 power n elements, and you can clearly see that power set, this 2 power n will be always greater than n for all n greater than equal to 0. So I can say that power set, cardinality of power set is definitely greater than, okay, the cardinality of set. This will always happen. Okay, so anyway, now what you can see, remember, this will always happen for finite or infinite set. This S can be finite set, this S can be infinite set. This we will study. This is known as Cantor Theorem. Okay, so this is basically the Cantor's theorem. This is the Cantor's theorem. This we will study in the theory of computation. Okay, this is the Cantor's theorem, that for any set, for any set for any set S, this S can be finite or infinite. Okay, finite or infinite. For any set S, basically the cardinality of power set of S, that is always greater than the cardinality of S. So this is a theorem, this is known as Cantor's theorem. So this power set cardinality will always be greater than the cardinality of set. Now why I am saying this, okay, where we are going to use this? Now you can use this fact here. Okay, in this question, for this option C, you can use this fact. So in the option C, what you can say, that this is option C. Okay, the option C is saying that what will be the power set intersection set. Okay, what can you say about this cardinality? Okay, so let's see. This is equal to power set of S. First of all, tell me, what can you say, what will be this cardinality? Remember, this is the intersection, means the common elements between S comma power set of S, the common elements. So definitely the number of elements here, that will be less than equal to the cardinality of S, that will be n. Okay, so this is the idea. The cardinality here, I can say, okay, let's call it LHS and let's call it RHS. Then you can notice that the cardinality of LHS will definitely be less than equal to n. Why? Because we are taking the intersection of S comma PS. Okay, so this intersection will be the number of elements that are common, those elements which are common between S comma PS, those elements which are common. So if you are finding the common elements, definitely the intersection will give you less. Okay, intersection will be basically a subset of S. Okay, so this is the idea. Basically this is the point, that if you have, okay, if you have this set A, let's assume this is the set A and this is the set B, then if I ask you what is A intersection B, A intersection B means this is the area. This area is known as A intersection B. Okay, now clearly the A intersection B cardinality will be less than equal to cardinality of B, because this whole area is B. You can notice this whole area is B. Okay, so this A intersection B area, that is definitely has less cardinality than cardinality of B. I can also say that this will have less cardinality than cardinality of A. So these two things we have. Now similarly you can say that this is the intersection of S comma PS, and S has less number of elements than PS. Cardinality of this PS will be greater than cardinality of S. So I can say, what can I say about this LHS? The cardinality of LHS will be less than equal to n. But what is the cardinality of RHS? The cardinality of RHS is actually 2 power n, and you can notice that 2 power n is strictly greater than n, that is strictly greater than n. So I can say that this RHS will have strictly more number of elements than this LHS. Okay, so because the cardinality of RHS is 2 power n and the cardinality of LHS will be less than equal to n, and 2 power n is strictly greater than n. So I can say that cardinality of RHS, that is strictly greater than cardinality of LHS. Okay, so that is the reason I can say this option C can never be true. This can never happen. Like, okay, this RHS has more cardinality, strictly more cardinality than LHS. So definitely they cannot be same. I can say they can never be same. So this option C actually can never be true. again for this option C, what I can say, this option C, I can say that this can never be true. This option C will never be true. Okay. Now let's see about option A comma B. The option A is saying that power set of power set is equal to power set. Again, this option A is also never true. This option A is also never true. Why this is never true? Because you can clearly see what this option A is saying. Option A is basically saying this. Okay, option A is saying that power set of S, this is same as power set of S. This can never happen. This statement can never be true. Why this can never be true? So let's assume your S has cardinality n. Then what will happen? Then definitely the cardinality of power set of S will be 2 power n, and the cardinality of power set of S, okay, that will be what? You can notice that will be 2 power n. Okay, so definitely this LHS has more cardinality than RHS. This is what I'm telling you in the Cantor theorem. You can notice here, this is the Cantor theorem. For any set, if you take any set S, okay, this set S can be finite or infinite. Okay, finite or infinite. If you take any set S, then definitely the cardinality of power set will be greater than the cardinality of set itself. Okay, so this is the point what I'm saying. So if you have two set, let's assume you have two set, like this is a set. Okay, this is a set. I can say what I can say. See, this is a set. This is the power set of this, and this is the power set of this. I can say this is the power set of this. So let me call it B. Now you can notice that Cantor theorem is saying that cardinality of S will be less than the cardinality of B, the cardinality of power set. This is what Cantor theorem is saying. This is the result of Cantor theorem. This is what Cantor's theorem says. This is what Cantor's theorem says. Okay, so cardinality of S is less than cardinality of power set. And you can notice what is this actually? This is now power set of B. Okay, if I assume this is B, if I assume that this set is B, then now what is this? This is power set of B. So now you can clearly see that the cardinality of B is less than, because if this is set B, then this is power set of B. Definitely Cantor is saying that cardinality of B is less than cardinality of, okay, power set of B. So here I can say that the cardinality of PS will be strictly less than cardinality of P of PS. Okay, it will always happen. It will always happen. So this is the idea that this will always have more cardinality. This LHS will have more cardinality, more number of elements will be here. Okay, this will have less number of elements. It will always happen. For every set it will happen. So I can say this option A is never true. Okay, so this is the idea. This option A, this is also never true. And you can also see this option A here also. So here if you find out what is power set of S, then how many elements will be there? In the power set of S you have total 2 elements. So in the power set of S there will be total 4 elements. Okay, so if this is your set S, then the power set of S will be this. And what will be the power set of this set? The power set of this set will be A, this 5, okay, this element, and you can notice this element, and this PS itself, and this PS itself. Correct? So this is the idea. Now you can find out that P of PS, you can clearly see this P of PS, this is not same as PS. These are definitely not same. So I can say option A is wrong. Okay, by this example also you can notice. From this example you can see that option A is wrong, option C is wrong, and option D is wrong. So these statements are never true. They can never be true. What about option B? Let's check option B. Option B is saying that power set of S intersection power set of S is equal to set containing 5. Okay, so let's check this option. So this option B, this is saying that power set of S intersection power set of S, that is equal to set containing 5. Let's see whether this is true or not. See, this can be true. If I take this set S, for example, let me take this set S, then what will be the power set of S? You already know. The power set of S will be 5 comma S itself. And what will be the power set of S? That will be, okay, that will be 5, set containing 5, set containing S, and set, okay, and basically this PS itself, and this PS itself. Okay, now what is the intersection of these two? What is the PS intersection P of PS? What that will be? So here you can clearly see that intersection. Okay, what are the common elements? Here you have 5 comma s. These are the two common elements. Okay, these are the two elements in this set. In this set only the common element is 5. This element is here also, this element is here also, so the only common element is 5. So you can clearly see this option B, this can be true. For this set S, this is true. So I can say if your set S, if you take this set S, then definitely you can notice that P of S intersection P of PS, this is basically equal to set containing 5. Okay, so this is correct. Option B can be true. But remember, actually option B is also not always true. This option B is not always true. If you take this set as, for example, let's assume this set as you take, set containing 5. Then what will be P of S in this situation? The P of S will be 5 comma S itself. Okay, this will be P of S. What will be P of S? That will be set containing 5 comma set containing S, also okay, set containing 5, and also this P of S. Now if you find their intersection, now if I ask you what is the intersection of P of S and P of S, what is the intersection of this and this? So the common elements, what are the common elements in these two? Now you can clearly see this 5 is here also, here also, this, so this 5 is common element. Okay, what else? What else is the common element? You can notice this S. What is this S? This S is basically this. Okay, so I can write like this instead of this S, I can write like this, because this is what S is. Okay, now you can notice this is also common element. This element set containing 5, this element is here also, this element is here also, so this set containing 5, this element also will be here. So you can notice this option B is also not always true. Okay, so the question is asking which is always true. This is what question is asking, always true. So I can say that option A comma C comma D, they are never true. Option A comma C comma D, they are never true. Okay, there is no set for which they are true, they are never true. But this option B, this is not always true. This may or may not be true. This may or may not be true. Okay, because we have already seen this is true, this option B is true for a set. This set we have already seen, for example. Okay, for this set option B is true, but for this set option B is false. So for this set I can say, what I can say, for this set option B is true, and for this set I can say this option B is false. So you can notice option B is also not always true. The question is asking always true, so there is no answer here for this question. None of the option is always true. But you can notice that, okay, the best answer, if you have to pick one answer, then answer you should select as B. See, B is not always true, but you can notice A comma C comma D, they are never true. Okay, B may or may not be true. Okay, so here if you want to say what is the answer, there is no answer. For this question, none of the option is correct. But in the GATE exam, you should not leave it blank. Okay, you should say that, okay, option B, you should tick mark option B. But the point is this, that no option is correct. Now let me tell you one more thing, that if all the elements are simple elements, basically, okay, if you have set, let's assume you have set B, let's assume you have set S, and in this set S, let's assume all the elements are simple elements. Simple elements means none of the element is set. For example, here you can notice this is a set, right? This is a set. The counter example for option B, in the counter example what we have done, we have taken a set which contains set. So if you take simple set means this type of set. If you take this type of set, if you take, okay, means simple set. Okay, so let me write this simple set. What is simple set? Simple set means no element is a set. Simple set means a set, okay, in which no element is a set, in which no element is a set, no element is a set. Okay, so for example, this is a simple set, but you can notice this is not a simple set, because, okay, here this is a set. So I am saying simple set means a set in which no element is a set. Okay, so this is a simple set. Now if you take any simple set, for any simple set what will happen? For any simple set what will happen? For any simple set S, this is what will happen. See, if your set S is a simple set, means like this type of elements you have, like a comma b comma c, this type of elements you have, then what will be the power set? In the power set you will have this type of element, like okay, there will be 5, okay, there will be this type of elements will be there in the power set. And what will be there in the power set of S? You can notice that in every power set 5 will definitely be there, 5 will definitely be there. Okay, now what else will you have? Now this type of things you will have, okay, this type of things you will have. Now you can notice the only thing that is common between these two, between these two, now remember this is not same, these are not same, this and this they are different. So I can say the only thing that is common is 5, this 5 is the only thing that is common. So I can say if S is a simple set, okay, so for any simple set, for any simple set S, I can say that power set of S intersection power set of S, that okay, the only common element between these two, the between this and between this, the only common element will be basically 5. Okay, so this is the result for any simple set. So I can say option B will be true. In this question, they should mention that S is a simple set. Means S does not contain any element which is a set. Okay, every element in this set S, that is a simple element. So in that case, option B will be true. So you can notice this option B may or may not be true. If set S is a simple set, then option B will definitely be true. So for this question, none of the option is correct, but the best choice is option B. Okay.